Okay, so yeah, so it seems that maybe we can start. Uh, yeah, so basically today we have a talk on quantum Lego expansion pack, and this is something that like I wanted to learn for a long, and and we have pleasure of having Charles here. So Charles basically, I mean, he has done lots of work in different areas, including like quantum error correction, quantum gravity, and so on, quantum information, like and yeah, I mean, so he did his PhD at Caltech, and then he was a Hartree Fellow at University of Maryland, and then he had a short stint at Caltech, and then he joined Virginia Tech as assistant professor, and and he has been working on like all these exciting things, and today he like he's going to talk about his work. So if anybody has any question, maybe you can unmute yourself and ask. And I mean, Charles, maybe you can start.
Sounds good. Thank you, Kishore, for the invitation and the kind introduction. So today I will tell you a little bit about this work on essentially computing weight enumerator polynomials from tensor networks. And this is the work that was in collaboration with Michael Golens, Brad Lackey, and Zita Wang. So let's start off with the basic things, right? So everyone here is interested in quantum error correction. So I trust you need no convincing that we think quantum error correcting codes are important and interesting. So they're a pivotal pathway to fast-forward quantum computing. But we can also, they also made their footprints outside of computing per se, right? They also made significant impact in, say, quantum many-body physics and quantum gravity in, say, topological order or ADS-CFT correspondence. So the quantum code that we're going to talk about today is essentially taken from Nelson and Trump, the basic definition. You pick a co-subspace in the physical Hilbert space, where the physical Hilbert space, you can think of it as being the space spanned by the qubits that we control in the lab. All right, and we want to choose this co-subspace such that the information that's encoded in there is robust against whatever error that occurs to my physical qubits. So alternatively, it's also convenient to identify the subspace using an encoding map. Let's call it V here. So in this case, we can define an encoding isometry that goes from, say, a logical Hilbert space to a physical Hilbert space, where the logical qubit is really the encoding information here. And the logical Hilbert space will be isomorphic to the co-subspace. Okay, so a common example that we see that everyone's familiar with is the stabilizer code, right, where we can generate the co-subspace from a group, an abelian group of the Pauli group. So and then I just take, let's call it S, and we can take the +1 simultaneous eigenspace of this group element, and I call it the co-subspace. Okay, so if I want to create the code that encodes k logical qubits into n physical qubits, I just have to pick a group that's of order 2 to the n minus k, and then that will create for me a co-subspace that's 2 to the k. So very concretely, here's an example of a 5-qubit code that encodes 1 logical qubit, where the stabilizers or stabilizer group are generated by these Pauli strings, where whenever we talk about x, that means the tensor product with the Pauli X operator and the identity operator. Okay, so once you have the stabilizer group, it's also easy to construct this encoding isometry from the code words. And in this case, it will represent a map that goes from 2 to the k dimensional Hilbert space to a 2 to the n dimensional Hilbert space. Okay. But then there is one additional parameter that's very important to understanding the code, right? That's the code distance. And intuitively speaking, that is the number of errors when the code can tolerate before the logical information becomes corrupted, right? More specifically, here by the distance we mean the minimum weight logical operator. And here, and for now, when I talk about weight, I just mean the Hamming weight, right? You count the non-trivial support, how many sites the operator has non-trivial support. So in this case, if you have XXII, that will have weight 2, or if you have this object, that will have weight 4. Okay. But despite the fact that we can simulate stabilizer or stabilizer states or the Clifford operations efficiently using classical computers, finding the code distance remains NP hard. And this is the case for polystabilizer code, right? So for generic polystabilizer code, you take at random, finding its code distance is going to be exponential in the number of qubits. But there's a smarter way of doing this, right? So if I know a bit more about the code, I can map this code into classical linear code, and I use some of the existing technology from distance verification. And then that can lower the complexity to e to the distance. But if we go beyond polystabilizer codes, there really isn't a very well-formed strategy to find its code distance. So I would say there is Revon. No. Okay. So today we'll start off from sort of thinking about this distance problem, but we'll also talk about more than the distance. And the strategy essentially is to compute these so-called weight enumerator polynomials. So these are general coding theoretic objects that are that's well defined for these general quantum codes that need not be stabilizer codes. And they contain important properties of the code. For example, if you construct these polynomials, you can hope to, of course, read off the distance. You also learn about how big the logical how big the code subspace is, right? The encoding rate, and you will also learn about, say, the logical error probability from such polynomials, as we will see in a little bit. And in addition to codes, you also learn about states. So for example, in the graph state literature, some of these specialized enumerator polynomials are known as sector length in graph states, and they can help encode important entanglement features. And later on in this talk, we're going to see that these enumerator polynomials also teaches something about magic or non-stabilizedness that's embedded in the state. And as we probably know, that these enumerator polynomials in the past have been used to generate linear programming bounds to bound the code parameters of error-correcting codes, and also to understand the performance of magic state distillation protocols. And today we're also going to see how they can be applied to decoding problems. Okay, so that is the strategy, and the outline is essentially first to sort of convince you that this weight enumerator polynomial is actually useful. By introducing a few applications, such as how to find the distance, and how to find logical or COSA error probabilities in service to the maximum likelihood decoding, and how to, for example, compute magic in the form of stabilized Renyi entropy. And then, of course, having all these good applications, we really want to be able to compute it, right? And that's when we introduce the formalism of tensor enumerator, and then combine with the technology of tensor networks that really allows us to substantially speed up the computation of these objects, which are, generically NP hard, but once you have the some structures, you can really speed it up. Okay. So yeah, also please feel free to interrupt me at any time during the talk. So let me just pause a little bit for questions if there are questions.
I think like, I mean, maybe we will discuss it, but these weight enumerators, I think they are used in like for deciding whether a code of particular parameter exists or not, right? There is weight enumerator, then dual weight enumerator, and you have this Mac-Williams identity, which like
that's right.
So basically, you use the same technology, but or maybe more, and use it in the context of like calculating distance and other things.
That's right. Yeah, exactly. Yeah, that was exactly the application of linear programming bounds and then distance. Yeah. So since you mentioned this, I feel like maybe I should mention a little bit of what we actually did. So essentially, distance is well known, but here we're going to also introduce other enumerators that's called quantum COSA enumerators that compute these COSA error probabilities, and we're going to talk about some higher genius enumerators that compute magic. There's a lot more in the paper, but let me just focus on these objects. Okay, so excellent. So thank you for the question. Please keep them coming. So what are they? So let's start with the simplest example, and these are the first instances of weight enumerator quantum weight enumerator polynomials. So they were first introduced by Shor and Flung in 1997. So formally, they look like this, right? Okay, so the first thing that we notice is that they're enumerator polynomials. They depend on a couple of variables, and then they also take in these M1, M2, which are large 2 to the n by 2 to the n matrices. So what we end up doing is that for these matrices, you compute some sort of the inner product with a polystring, and then that computes the coefficient in front of these monomials. And there's, each of these variables is raised to the power of whatever the weight of the polystring is. Okay. So there's the A enumerator, and then there is a companion enumerator, let's call it the B enumerator, which is related to it, but it has a different but similar taste to it. But what's important is to note that, exactly as Kishore mentioned, that they come in pairs, right? There is a McWilliams identity, that there is the duality relating the A to the B enumerator. So if you know one, you know immediately how to get the other. So here's an example of that, where if you have a enumerator over q dits of local dimension q, this is what the relation is going to be like. Okay, so let's get a bit more intuition what these things are telling us. So let's think about the example of applying them to stabilizer codes. Okay, so if I take these M1 and M2 to be the projection operator onto the stabilizer code subspace, then I can simplify the expression above and then massage them in the following forms, where these AD are just the coefficients to the monomial where Z has power D. And it turns out that up to normalization factors, AD is simply counting the number of stabilizers that has weight D. Okay, and similarly, BD here is counting the number of normalizers with weight D. So this is counting a number of logical operators, including logical identities in the stabilizer code. So together, what we're generating with these enumerator polynomials is a weight distribution of all the relevant operators that we usually think about in stabilizer codes. Okay. Now, to compute its code distance is then very intuitive, right? I look for the smallest d for which BD minus AD is greater than 0, and that will pick out when do I start having a non-trivial logical operator that has weight d. Okay, but what's interesting is that this thing also extends beyond stabilizer codes. So this theorem remains valid for general quantum codes, which shown by this paper over here. So you can, so just by checking for what d this thing greater than 0, you can figure out the code distance for even non-stabilizer codes, just anything that's very general.
So Charles, if I might ask a clarification question. So
Yes.
what are the Z's and the W's here? So sorry, I might miss that.
Yes, because right. Good. So they're just variables, right, in a polynomial like x, y, z. So this one's just I just picked it to be z and w. Yeah.
All right. Thanks.
Good. Thanks. Also, I should mention that I don't have that little window of who is speaking, so I'm sorry if I don't recognize who's actually talking.
Yeah, it was Andrew, but yeah, no worries.
Okay, sorry. Yeah, thanks. So one other thing that we're going to recognize is that this weight distribution is is the coefficient that matters, right? That's telling you the weight distribution, and this W here actually doesn't add anything else to really add any information to this polynomial. So you can sometimes people just write it without the W, and then if you want the W, you can always homogenize this polynomial by adding it back in, such that the total degree adds up to n, but it's not a big deal. Okay. All right, so so what are the applications? So let's suppose you have this, right? You have this polynomial. Now you have two variables, w and z, and I think Andrew had asked this question, like, well, what are you going to do with these variables then? So one of the nice applications is to compute logical error probabilities. So for example, if you have a code where each individual qubit is going through this kind of depolarizing channel, And then you can just plug in these error probabilities for the identity error and for the XYZ error into the polynomial into W and Z. And then in this case, it just computes the probability that the errors will conspire to form, the errors will lie in the logical identity. Whereas, if you plug it into the B enumerator polynomial, it will just compute for you the probability of having a trivial syndrome error when you are subjected to this kind of IID depolarizing noise. And therefore, if you take the B and minus the A, right, that computes for you sort of this undetectable logical error rate. So what I think is a neat application of this is to recognize that there's the B and an A are constrained to each other by the McWilliams transform. So let me talk about this in a more realistic example. So let's imagine ourselves encoding some state information into a code. And then I'm going to pass this code, this encoded object, through a noisy channel, and the noisy channel has like IID depolarizing noise. And then after it is passed through the channel, I'm going to do a syndrome measurement, right? If the syndrome is trivial, I keep it. If the syndrome is non-trivial, I detected some errors, I'm going to throw the state away, right? So so this is the kind of thing that we usually run into in communication channels or in magic state distillation. So after you've done this, you count the number of states that you kept, and you ask, what's the probability? What's the fraction of states that actually suffer from a logical error? And that's calculated by this parameter P sub L, right, which depends on P. But then it is essentially a very simple function A and B. And by McWilliams identity, we can figure out that A and B are related precisely by this equality at the points when P is equal to 1/6, where K is the size of the co-subspace. Okay. So what it means is that if you plot these logical error rates as a function of P, all of those curves must cross at this point where P is equal to 1/6, and P sub L is equal to 1 minus 1 over K. So here are some examples of the distance 11 color code and some sort of rotated surface code. So they're all like order 50 to 100 qubits. And by computing their enumerators, you can figure out this function right? P also. Sorry?
I was saying, like this also gives you threshold information then, right? Yeah.
Exactly.
Nice.
Yeah, exactly. Good. So So in this case, we computed the enumerator exactly. So all of these curves are precise analytical results. You plot them, and you realize all of them cross at a single point. And that's precisely this McWilliams, the consequence of this McWilliams identity. So a natural corollary of this is that if you have a class of codes that all have the same size in the same dimensional co-subspace, and you can just increase their distance or whatever. This is the only restriction. And if it has a error detection threshold, then it must be 1/6. So here, this is what we see. Essentially, they're all crossing at 1/6, and P equals 1/6. So perhaps there are some. Okay, let me talk about applications a bit later. Are there more comments or questions?
Yeah, just a quick one. So in general, can I think of finding the value where there crosses, like if I have like this multiple like codes like with different distance and all that, can I think of finding this point where they cross as like solving a system of polynomial equations or something like that?
Yeah. I think we can think of it like this. Yeah.
Okay, interesting.
And the McWilliams identity actually, yeah, exactly. So the McWilliams identity actually ensures that there's always the solution here. Yeah.
Awesome. Thanks.
Yeah, thanks. Great. So there are no more questions. Let's move on. So that was one application of the computing the logical error probability with a trivial syndrome, right? So, but then for the more general decoding problem, we will also like to compute the conditional probability given some syndrome that may or may not be trivial, what's the probability of the error actually lies in some coset? So for instance, you can think about like a coset generated by some logical x times some z error, right? So if you have measured a syndrome that's consistent with this error, what's the probability of that? And if we know what this is, right, for different sets of cosets, then we can simply just undo the error that has the maximum probability in the decoding process, right? And this is nothing but the maximum likelihood decoder. And so with enumerators, we can actually compute this exactly. So remember how we were computing the thing before, just by plugging in 1 minus 3p and p into the variables. Now you just change slightly different forms of M1 and M2, and you're done. Okay, and that essentially solves it. So if you do have the enumerator polynomials, it also solves the optimal decoding problem. But since we know that the optimal decoding problem is sharply complete, it must mean that solving for the enumerator polynomials is generally very, very hard. Okay. And now, so that was general coset and conditional, general syndrome. But we can also think about more general error channels, right? So far, we've been looking at depolarizing noise associated with these short or flat enumerators. But if we have different error channels that are applied to my physical qubits, we can still derive other forms of enumerator polynomials that depend on the structure of the error channel. So, for example, if we work out, let's just focus on the second inequality. The second equality. If you try to compute, say, the average coset error probability that depends on that's conditional on a particular syndrome, eventually, and then your error channel has some breakdown into the Krauss operator that's in terms of these k's. You can show that the error probability actually just depends on this structure. And the thing in the box actually looks like the coefficient of our type A enumerator polynomial. And this thing in the denominator actually looks like the coefficient of the type B enumerator polynomial, right? So from this, we're getting the clue that, oh, actually, I can define more general enumerator polynomials just from the structure of the error channel. And indeed, that's what's going to happen. So in this LEGO expansion pack paper, we were able to introduce these more general enumerators. And they look just like this form, where now instead of having some W and Z, you can have a more general set of variables that depend on the structure of the error channel. And then you have some weight function that can, instead of the Hamming weight, that can depend more generally on the structure of the error channel. And once you have this kind of enumerator, you can still just plug in some error probability associated with the channel. I can still get out this kind of a conditional error probability. So let's, and once you have this, of course, you can use that to construct your maximum likelihood decoder. And to give you an example, by the way, yeah, so these two A and B also comes in pairs most of the time. So in this paper, we're able to prove that a lot of them do satisfy a McWilliams-like identity, as generalized as what we saw before, but we were not able to prove it for all of them. So I don't know whether they exist or not, or maybe it's just we didn't figure it out that. So I invite all of you to look at it if you are interested. Okay, so let me give you an example. So suppose we're now considering a more general Pauli channel that can have asymmetric errors, like with these x, px, py, pz, physical error probabilities, and then let me apply it identically to all the qubits, all the physical qubits, and from this procedure that I described before, but I didn't explain in detail, you can read out the fact that you can, from the structure of the channel, you can figure out that there are, okay, you can probably see this, right? There are 4 types of things that I need to incorporate. One of them is dependent on the other 3 things. So this the W, which we mentioned earlier, was useless. But to make things symmetric, let's just keep it. And then there are 3 other variables, x, y, z, that's associated with the poly x error, poly y error, and poly z error. So from this kind of structure, we can essentially read off the form of the enumerator polynomials. And then from this thing that I didn't talk about is that you can also read off the form of the weight function from the error channel. And the structure of the weight function now is, instead of computing Hamming weight, it's going to have these forms where for x you raise it to the x weight of this poly string, where you just count the number of x's that appears in E, and here is you count the number of y's, you count the number of z's, and that's it, right? So you just plug this into U, and then plug this weight function into W, the weight function E, comma F. Then after that, you will get a new enumerator polynomial that looks like this form. Okay. And then by plugging in these error parameters, error probabilities into the enumerator, you will still get back things that we wanted before, which is this conditional error probability. But because of the time, I don't really have time to describe in all the details how exactly to arrive at this, but it's actually fairly simple. So this is described in more detail in the paper. Let me just pause a little. Oh yeah, so one more thing to mention is that this is actually called you can recover using our procedure. You can actually recover, in this case, the complete enumerator polynomial, which were defined first by Hu et al. Okay, let me pause again for questions.
So what exactly are Lego? Like, I mean, let's say in your paper, like, I mean, what exactly are the Lego blocks? Lego blocks, like, I mean.
Oh, the Lego blocks. Yeah, I haven't talked about them. Yeah, we will talk about them very soon. Yeah.
Okay, we'll talk about it. I was thinking because I mean, do you mean this weight enumerator or something? Okay, anyway, yeah. Okay, I will wait for that.
We'll get there soon. Yeah.
Okay.
Yeah. Thanks. Yeah. Other question?
I mean, other thing, I don't know, it just crossed my mind. So like, so we recently, like with Andrew, like who was asking question, we gave this formalism for quantum error correction, which kind of generalizes all the flocate codes, dynamical codes, all of the codes basically using process tensor or quantum comb. So you can think of them as like multi-time point channel, and it captures non-Markovianity, which is present there, like, I mean, the system and all. I was just wondering, like for general process tensors, like, how maybe one can work out, like this A and B.
Yeah, that will be very interesting.
Yeah.
So Brad has one more follow-up paper that he wrote with his student, which deals with the space-time circuit error, and then from there you can sort of define something that looks like an enumerator. But I don't know whether it will, the quantum content. Yeah, that is very interesting. It will be really nice to think about that further.
Yeah.
Okay. So let me just make a couple more remarks before we jump into the Lego part. So far we've been talking about, we've had in the back of our minds that we're doing stabilizer codes, right? But remember that the enumerator is actually defined for general codes. So it turns out that we also did in this paper that you can apply this technique to the codes that have non-abelian stabilizer groups that are called XP codes. And then you can use the enumerator-based maximum likelihood decoder for those as well. And beyond coding theory, right, you can also use enumerators to compute the magic that's present in the quantum state. So for this, we would need something that's called a higher genus enumerator. And essentially, it's just by taking, a tensor copy of you can take 2 tensor copies of the code and you plug it into M1 and M2. And I'm not going to go into the details, but essentially, it turns out if you work just by staring at the expression, you can figure out that the genus G enumerator evaluated at a special point at U equals 1 is actually just a Renyi stabilizer Renyi G entropy that people have been using to compute magic in quantum many-body systems. Okay. So now to the central questions, we talked about all these nice things that we can get from enumerators if we can have them. But they're already hard to compute in general, right? It turns out that for certain states, like the GHZ state, of course, we can compute them just by hand. But others, we would really have to have more structure. And if we do brute force, this is gonna scale exponentially with n minus k, right? For at least for stabilizer codes, it's gonna scale as something that looks like 2 to the n minus k just to get the A-type enumerator. And for general the enumerators, we're not going to be able to get anything that's past 30 qubits, essentially. That's obviously not enough to do anything useful. So the question we would like to ask is, how do we speed this up? So one of the things that we can realize is that sometimes this projection onto the code space, of course, it's given by the encoding isometry and times this dagger. Now, if the encoding isometry is coming from a tensor network, then perhaps I can just compute the enumerator for each tensor and then trace together connect all these tensors together, and then eventually I can get the enumerator of the entire thing, right? So that is the general idea that goes behind this work. And in fact, so what I'm going to talk about are primarily based on technology developed by these two papers. But then there's a separate paper that actually came before us by Farrelly, Tuckett, and Stace that also has a tensor network technique that it turns out they compute the short Laflamme enumerator for a class of codes called tensor network codes, which is a subset of polystabilizer codes. So although the two things are based on different ideas, they're in spirit, the idea of breaking this big problem into smaller pieces, solve them, and put them back together is very similar. But of course, the thing we're going to look at now is also very general and applies to all the different error channels and applied to more general codes. So let's now talk about that. So first off, quantum Lego. Okay. So let's look at the examples. So let's first start with the construction that perhaps I can just build up a code with these smaller components, and then I can compute the enumerator of each such small component. So here's an example of a quantum Lego block, right? So and by that we really just take you can take any small code, but here we took a 5-qubit code, and then you take its encoding isometry, which maps you from a 2 to the 5th dimensional Hilbert space. And then you can expand this isometry in the standard basis, and it will get out a tensor for its coefficients. And then for each index of the tensor, I can draw this graph. For each index of the tensor, I'm going to assign a leg to it. So in this case, the top leg is going to denote the logical degree of freedom, and then the other 5 legs are going to denote the physical degree of freedom. And this encoding map is just captured in this graphical form. And the stabilizers and the logical operators of this code are just manifested as symmetries of the tensor. So for example, if you act ZZZ on these three qubits, it's going to leave the thing in the object invariant. It's the same as if you contract some sort of tensor that's associated with the poly Z on these 3 legs, on these 3 indices, then you're going to get back the tensor itself. Okay. Now, so we can now start gluing these Lego blocks together to make a bigger code. So here's a very simple example. And so let me take 2 of them, and then I can glue them by just taking these 2 qubits. Let's just think of them as physical qubits. I project them onto the Bell state, and then I throw these 2 qubits away, right? And whatever I'm left with are these 1, 2, 3, 4, 5, 6, 7, 8 physical qubits. And these remaining 2 things are, remember, they're the logical qubits. So this thing represents a encoding map from 2 logical qubits to 8 physical qubits. So it's an A2 code. And you might be wondering, well, how do I figure out like its stabilizer and other defining features? Well, actually, it's very simple. So if we know the stabilizer of, say, one of the block here, let's say the left block, we remember that ZZZ is a stabilizer on this left code. to generate a stabilizer of the entire thing, I just have to find a matching stabilizer on the right code as well, such that the two operators acting on this connected edge is matching. And whatever operator that's acting on these remaining dangling legs is a stabilizer of the new code after we glue them. And we can repeat this process for all the stabilizers. Of course, that will help you generate the entire stabilizer group. But of course, there are smarter ways of doing it, and that's only polynomial instead of exponential in the number of qubits involved. Okay. Any questions for this construction?
So like Charles, can you go to previous slide?
Yes.
So you mentioned that like once you have I think the one even before that.
Oh yeah.
Yeah, here. So you said that the symmetry is basically like help you determine which one are the stabilizers and which one are the logical operators. So is it like what symmetry? Will you explain? Like which one do I call as stabilizers and which one do I call as a logical operator?
Oh, excellent. Okay, so the thing I was trying to skip ahead because there, but it's a very interesting question. So for example, in this, so let me first talk about symmetries, right? So symmetries is just, if I think of this as a state, if I flip this bra to a kit, okay, and then I can think of this thing as a state. The symmetry is just whatever operator is acting on the state leaves the state invariant. And so it doesn't have to be poly. So in this case, right, you have a stabilized group that acts on the state. There's obviously a symmetry of the state, but you can also have other operators that are not polys or not Clifford that leaves the state invariant. So they are also symmetries of the state, and then the symmetry of the tensor is just whatever you inherit from the state. Does that answer your first question?
Okay. Yeah, but which symmetry you call stabilizers and which one you call logical operator? Is it same as what we use in
good.
regular?
Yeah, right. So for the second one is what do you call stabilizer? What do you call logical operator? Logical operators are the ones that act non-trivially on the logical leg. So remember the one that's acting. Yeah.
Sure.
So this one's yeah.
So basically, it's basically similar definition as what we have in the, let's say, stabilizer formalism.
Yeah, that's right. Except in this one, you can also incorporate the other things, right? For example, for all of these codes that perhaps you have swap, you have like some rotation, phase rotation gate. Those are also symmetries. Yeah.
Okay,
but I will not be talking about them here because that gets too complicated.
Thanks. Yeah.
Thanks. Yeah, this is an excellent question. Yes. All right. So let me continue. So now knowing how the stabilizers are generated through this kind of operator matching procedure, let's sort of capture this idea to construct weight enumerator polynomials. So suppose the code that I want to generate is like gluing together two 422 codes where each 422 code has like the usual CSS code that has this kind of stabilizer group. And I'm going to represent each of them with this orange blob where these two legs represent the logical input qubits and these four legs represent the physical qubits, right? And so now if I glue these two together, I can try to figure out what's the resulting stabilizer group, right? So I do the same, for example, if I just put down z here, by operator matching, I know that I must put down z here to produce a consistent stabilizer. So I add that to the group. And then I can repeat this for x and y, the identity, and we'll find that this has to be the stabilizer group after I do the gluing. Now to count the enumerator, we do sort of the same thing, right? So let's define a tensor or a vector enumerator called aj of z, where it's basically it's a polynomial, it's a tensor of polynomials. And what it is doing is that it's asking the following question. Suppose you have an identity that's acting on this leg that's to be glued with the other object. How many stabilizers do I have that had weight 0 acting on the remaining 3 legs? Right. So this is what A0 is. A0 identity is. So the J takes value of identity XYZ. And the D goes from the 0 all the way to the number of legs that are not glued. Okay, so in this case, A0 is saying, well, okay, there's only the identity operator. So there's one operator that has weight 0 on the other 3 legs. So this guy has to be 1. And then there's no other operator that acts as identity on this leg. So everything else is 0. Okay. Similarly, we can repeat this exercise and we ask, well, what's the stabilizer distribution for all the stabilizers are acting as X on this leg? Well, there's none that has weight 0 on the other 3. There's none that has weight 1, and the only one that works is that has all X, so it has weight 3 on the other 3 legs. So this thing is. So if we repeat this exercise, we're gonna find that the vector enumerator is gonna look like the following form, where the first one is equal to 1 and the other one is equal to 3. And we do the same thing for the right blob. And then we glue them together by just doing this trace of summing over repeated indices, and you can see that this precisely reproduces for you the what we expect from our example above. So more generally, right? So that was a very simple example for a stabilizer code. More generally, we need to extend this former definition, the definition that I showed on the previous slide a little bit. But it's essentially the same idea. You can define these things. I'm just flashing them so you know what it looks like, but I'm not going to explain what it actually is. But intuitively, it's the same thing. And then it has a few sort of properties, right? So, for example, it's covariant under local unitary transformation. So if you transform the code on the local unitary, it's going to mostly leave this enumerator invariant, but you pick up an additional matrix that permutes these index degree of freedom. And it also satisfies the Williams identity. So formerly we had this A, which counts the stabilizer, but you can also define a B that counts the normalizer, and the two are related precisely by McWilliams identity. There is some additional thing that goes on in the vector index where you have to do a discrete Wigner transform to make it precisely equal, but everything else is very analogous to the scalar case. And by tensor enumerator, you just go to higher rec, right? And then you can define that. So, for example, here's a construction of the surface code, but in terms of those 512 Lego blocks that we've seen. And essentially, the strategy here is just you compute the scalar and vector enumerators, or sorry, the vector and tensor enumerators for each of these blocks, and then you glue them together. And after that, you get a tensor network, except the tensor components are not complex numbers; they're polynomials. And then you just construct this tensor network, and after that, you can get the A-type enumerator of the surface code, and that's how we scale it up to around 200-300 qubits. And after that, you can always do the McWilliams transform to get the B-type. Okay. So the complexity of constructing this tensor is, basically around approximately the same as what we intuitively expect for the usual tensor network contraction. It's going to scale exponentially with the amount of entanglement that's present in the code word. So let me just show you a picture. Show you a table. So if you say have a tree architecture in your code, let's say you have a concatenated code that's highly symmetric, it's going to give you, say, a log n or linear in the number of qubits. Okay. On the other hand, if you have a holographic code where you have a hyperbolic surface code that has sort of this kind of 2D hyperbolic geometry, then it's going to scale polynomially with the number of qubits, where alpha depends on the hyperbolic tiling that you're using. And for these Euclidean lattices, like the surface code, is going to be a sub-exponential in number of qubits. And then, of course, for general codes, you expect it to be just exponential in number of qubits because, we can't solve an NP hard problem in polynomial time. Right? But even for these practical, for the sub-exponential speed, say for a 2D surface code, you can still just run it on a laptop up to 300 qubits. Yeah, so it's still a tenfold increase over what we could previously do for using just doing brute force.
So like 200 to 300. So let's suppose I want to, figure out whether so let's say, like recently this IBM developed this bivalent bicycle code, and they have, like around, I mean, there are CSS codes, and they are like, they have around 200 physical qubit of that range, like 100, 200, like of that range. So let's say I want to, like rule out, like figure out, like what kind of codes are not. So I'm thinking from a linear programming bound perspective. So, like, I mean, so I want to rule out, like what kind of codes are not possible. Like using this Lego technique, you're suggesting that, like maybe on a laptop, I can do up to like 200, 300, or?
It's hard to say. It very much depends on whether I know how to construct the tensor network or not.
Okay.
So far, I coded all the tensor network by hand, and that took a lot of time. So we really need like a coding expertise to make this automatable. And then after that, I think we can do something like the more practical. Yeah.
I see. Yeah, because people are trying to like come a bit better and better, but I think it would be nice to rule out certain region that like you cannot go beyond and so on for this family of codes. I think related to this, like I'm just trying to understand. So you basically you calculate all the like, I mean, A type enumerator using your Lego blocks, and the B type enumerator you just use Mac Williams to find out that.
Right. Yeah.
Okay. I see.
Yeah.
Okay.
The B type is usually harder to compute because it has more things in it. But you can also mix the A's and the B's for subsystem codes. That turns out to be very useful as well. But I don't have time to talk about it today. This is still a very interesting subject. Yeah.
Yeah. I mean, like normally when we do like LP bound, we also do this thing called quantum shadow enumerator, right? I mean, which also can be found from the ATAP. So like, I mean, like, is it like, did you look at like how to find shadow enumerator directly from the Lego blocks, or like, I mean, there exists an identity like which gives you the shadow enumerator starting from A type enumerators. I mean, but
yeah, I think it should be. So I have not really thought about it, but on the formalism level, it should be very straightforward.
I see.
So I don't think, I don't think it would be a difficult adaptation at all. Yeah.
I see. Okay.
Yeah. Thanks. All right. So so the previous examples that we saw were like, if I know how to build a code from smaller components, like from these quantum Lego, or you have these tensor network codes or holographic codes, you know that it breaks down into these smaller components, and then you can apply the enumerator technique. But of course, if you just have some stabilizer code or some LDPC code, we also provide a set of procedures. And essentially, you can just do a substitution, a clever substitution of the tensor graph, each node in the tensor graph by a suitable tensor. The thing in the paper tells you exactly what tensor to construct. And then you can do that for more general codes that perhaps you were playing with. It may not give you the best decomposition in terms of tensor network, but it will give you a tensor network decomposition. And then after that, we can just apply the same technique that we'll be using for the tensor enumerator and can compute that. Similarly, you can do the same for the graph state or cluster states. So for 2D cluster states, if there are any takers who are interested in computing their enumerator, to go for it. So just to summarize what we have done with this what we have now with this tensor network algorithm is that now for all quantum codes, we have a way to compute this weight enumerator, and that's in some cases is even exponentially faster than what we can previously do. And if we split the set of quantum codes into polystabilizer codes, and those are not polystabilizer codes, for the ones that are out here, we now also have a way to compute code distance using the enumerator polynomial, and they're substantially faster than what we had before. And since they're the only algorithm, it is the only algorithm available other than brute force, it also makes them the current best algorithm for such tasks. If we further divide the set of stabilizer codes into degenerate and non-degenerate codes, for non-degenerate codes, because we know that distance scales as the amount of entanglement that's in the code word. So in this case, at least in the scaling, we can show that the complexity is still going to be e to the d. So you're not going to get much of a saving asymptotically. But for degenerate codes, there could be some more improvement compared to a naive classical approach. So if I because there, for degenerate codes, there could be cuts in the code in the tensor network where the entanglement is a lot less than the distance. So in that case, you can have a complexity is a lot less than the actual e to the d. So an example of this is perhaps by considering the quantum compass code, where some, you can you gauge fix or bake in shortcode in some particular gauge, and then depending on how you fix the gauges, you can get complexity that ranges from square root n all the way to e to the square root n, and everything in between. So this is potentially an area where this tensor network technique can provide even further speed up for distance verification. So to summarize, what we have looked at today is primarily an algorithm that, using quantum Lego, if you know how to break down a large code into smaller components or construct a large code from smaller components, we can use this tensor weight enumerator technique to speed up its computation, and that constitutes the current best algorithm that we know for general weight enumerator polynomials. Once you have the weight enumerator, you can do all sorts of nice things with it, as we explained earlier in the talk. For instance, for all quantum codes, you now have a way to compute their code distances. This is especially useful if you want to study non-stabilized codes, but even for stabilized codes, for degenerate stabilized codes, there's a lot of potential for speed up compared to a classical approach. And then we can also apply this. Once you have the enumerator, you can also plug in all these error probabilities, right, to extract logical errors, potentially to compute the thresholds, all these sort of things. And you can do so at least, efficiently for IID errors. So IID single qubit error channels, then you can do it for all, those error channels. The scaling that we showed you earlier in the table is going to be roughly the same. Yeah, so we also applied this to some XP code stuff to show that they can work for non-Clifford stuff. Finally, you can also use it to compute magic. So it would be interesting to see whether it's any better, or perhaps any better compared to the existing algorithms that we have, or whether this McWilliams identity can teach us anything interesting about magic. Okay. So going forward, there's a lot of future directions. So on the computational front, right, we can apply what we already have. Perhaps in combination with Monte Carlo methods, we can compute more accurately or more efficiently the Thorne thresholds of various codes. Because earlier on I mentioned that we can just analytically compute many of these logical error probabilities as a smooth curve, right? So that's a lot better. We have thought about generalizing to space-time codes, haven't had the time to do it yet. It would be very nice to think about it more. And also generalizing to correlated noise. On the coding theory front, there's some more work about applying these enumerators and combining them with some existing knowledge in classical coding theory, and perhaps mapping it to some classical spin models, which will allow us to intuit the structure of these enumerators. And finally, there's some practical applications, right? So because these enumerators are good for extracting the properties of codes that are usually hard to get. So what we have done before was that we taught a machine to play with quantum Lego. We wanted to contract codes in nice ways such that it can produce a code that has nicer properties using reinforcement learning. But the major bottleneck is actually evaluating how good the code is. So with this sort of tensor network technique, by applying that to this kind of learning cost function, evaluating the cost function in these learning processes, you can hopefully scale up, from where we are now to perhaps hundreds of qubits. And then finally, distance verification for LDPC codes. So I was talking about how we are still not at the stage where we can just give me a code, I'm gonna write some lines of codes and immediately evaluate polynomials yet. I'm not an excellent coder, so I code everything by hand, but at some point there's got to be a software package that make it widely available to everyone. So once we have that, perhaps we can use it for distance verification for actual useful quantum LDPC codes that are hardly degenerate. Okay, so thank you very much.
Yeah, thanks, Charles. This was a very nice talk, like very pedagogically explained. So yeah, at this point, if anybody has any question, please just unmute yourself and you can ask Charles.
Yeah, so since you mentioned about generalizing it to space-time code, I'm wondering, if you could like just, generally do this weight enumerator on like circuit level noise, right? Like, so if you have an n qubit code and circuit depth k, then you have like this nk, you enumerate over like this nk qubit
Yeah,
Pauli's.
yeah.
So I don't know, like um what do you think like we can get from that, like by like from the enumerator of like like the circuit level noise, like could we like I don't know, like perhaps learn, I don't know, like the fault tolerant property of
Mhm.
that circuit, or yeah,
Yeah,
I'm
yeah,
just
exactly.
yeah.
Yeah. Sorry for interrupting you. Please go on.
Oh yeah, no, I'm just wondering if you have any comments on that. Yeah. um
Yeah, exactly. I haven't been looking at it for a while, but I believe Brad has a paper. That's the paper I mentioned earlier. That he had a paper with his student where they. So the problem with with the circuit level enumerator is that we can totally define it, we can totally compute it, but we haven't figured out a way to compute it efficiently. But for small sizes, they have already done it for these magic state distillation protocols where they have circuit level errors, and then they can count the different error paths, and then you figure out, you can use that to sort of optimize some protocols, as far as I know. Yeah, but certainly I hope that there will be more applications coming out of that. I don't think this is nearly as well as understood as I hope to understand it. Yeah.
And so another question that I have, so you mentioned that like you need to be able to write your encoding isometry in terms of tensor network representations, or in order to use the tensor network enumerator. So I don't know, like it seems to me that you should be able to always do that, because like you could like just
Yeah.
write that, like sum over like this V and all the legs, over all the legs and stuff. Yeah, I'm just wondering, like, like is like what's the case where we are not able to write it in that form?
Uh, there isn't. Oh, well, I mean, at least for stabilizer codes, where as long as you have stabilizers or checks, right? Then for all those codes, we essentially give you a way to do the a very explicit decomposition into tensors. But if you have something that's perhaps generated by sensors, I don't know, like someone gave you a huge matrix and that didn't tell you anything else, and this is the encoding circuit. Uh, Find me a decomposition in a tensor network. Maybe that's a lot harder. But for all the practical, for all the codes that we see so far, um, all these should suffice.
Okay, all right,
Yeah,
sounds good. Thanks.
yeah, thanks.
Okay, so I think maybe I will stop the recording now, and let me thank Charles once again for this beautiful talk. Yeah, let me stop the recording. I mean, if some people have question, maybe they can still ask and all, but again, subject to Charles' availability.